All right, let's look at the second section of functions. So this first problem says this table compares the initial amount of fuel Li Jing's car had and the total distance she traveled using that amount in several different occasions. Can the total distance be represented as a function of fuel? So the key word it's asking is, can it be a function? Is this a function? And the way we test this and see if something is a function is if every input has exactly one output. This is the way it works in the realm of equations. Every input has one output. And you can see they have a table here that represents what's going on. The way to test this, again, is to see if the input has one output. The things on the left, almost always, every single time, we're going to be inputs. We're using fuel, and the fuel is helping us figure out how far she was able to go. So I actually made a table like this myself. That's interesting. This is the input, because that's what we use. We use how much fuel that we've been using. And the output is what it tells us. By saying we went 30 liters, it shows that she was able to go 100 kilometers. That's the output. So good. Good. So the question is, does every input have exactly one output? We'll see. So 30 has 100. Okay. There's another input. It's also 30, which is interesting, but that also points to 100. So 30, although it happens twice, still only has one output. It only has the output of 100. Could seem misleading, but no, it is. It just every input has one output. Now, if this wasn't 100, this was say like a 40, then for sure this would not be a function, because using just 30 liters, she was able to go 100 kilometers and 40 kilometers. That doesn't really make sense. How could someone do that? And that's kind of the reason why we have functions in the first place, to see if things can even make sense intuitively. So if she was able to go 30, if she has 30 liters, she's going to be able to go 100 kilometers. Okay, now if she has 35, she can go 120. There's another instance where she had 35 liters that also went to 120 kilometers. So it's kind of like it's showing that there's kind of accuracy in what's going on here. It's every single time she puts in 35 liters to her car, she gets 120 kilometers out. So it's a very direct ratio. Every input has one output. Every single time you press the 2 button on the Coca-Cola machine, you only have to pay 75 cents to get that Coke. Every single time you press that button. You might press it a bunch of times, but you only got to press it. Every single time you press it, you have to pay the same amount. Okay, so 40 goes to 140. That's good. There's 45 goes to 160. There's no other 45s. 25 goes to 90, and 20 goes to 80. So every input has exactly one output. Okay. Now, there's some instances, it doesn't look like there's anything else to look at here. Every input goes directly to one output. And that's just function. It works fine. So because it works, because every input has exactly one output, we would call this a function. This is a function. So in other words, in answer to the question, the answer would be yes. Cool. Another instance where we might run into something that's a little bit strange is if this was like, for example, if you had 140, let's say that was 140, and this is also 140. You'd notice that 40 goes to 140, and 45 goes to 140. They both go to 140, but that's okay, because they're separate two inputs, but they both have exactly one output. They both have one output. Like the 40 has 140, and the 45 has 140. It doesn't matter, they both are the same, but they both only have one output. So it's okay if some of the outputs are the same, if some of the distances, some of the kilometers are the same, because they just need to be, every input can only have one output. If you were to press the 2 button on the Coke machine and it gave you, instead of 75 cents, and you punch the 7th button on the Coke machine and it gave 75 cents, that's still fine. The soda machine still works. So this is all right. Okay, actually, before we get to domain, let's look at how this looks like in the realm of graphs. When you try to figure out if something is a function, and in terms of a graph, you want to figure out if every input has one output. And we can kind of check to see if this is the case here. Let's see, the inputs are x. Again, x is input, and y's are outputs. Let's see if that works. So if I plug in 8, if I choose the 8 button on the soda machine, I get, let's see, that's about 2.5. I guess something like that. So that seems like that's roughly about what's going on there. It's not precise, but it's close enough for our purposes. And so that's that one input has one output. If I plugged in 7, I would get 1 and 4. I get 2 outputs for one input. If I just plug in 7, I get 1 and 4. Maybe if I make this clear, I choose this one input, choose input 7, and I get 1 and 4 as the output. So that means there's 2 outputs for one input. Which means one input gives 2 outputs. Oops, excuse me, hit the home button. Outputs. That cannot be. We cannot do that. Another way to think about that in terms of the equation of the numbers we had before is that it'd be 7 links up to 1 and to 4. This cannot be. This is bad. This means it's not a function. Another way to think about this in a way, so we say, actually, let's write it down. This is not a function. So our answer is no. Another way to think about this, and a faster way to do this, is something called the vertical line test. If I draw a vertical line through the graph, all the way through the graph, and if that vertical line ever touches 2 points at once, then it is not a function. In this case, I drew a vertical line on x equals 3, and I hit a point here and a point down here, which means it can't be a function. And over on the 7, if you draw a vertical line down here, it hits 1 and 4 and 1, or 1 and 4. So that also is not this. The vertical line test shows this is not a function. Even though that if I drew like a vertical line down at 8, it would kind of work. It only hits at 1 point. When I draw a vertical line and hits 2 points, then there's a problem. Now let's for another example for the vertical line test. If you were to draw a line and it went kind of like this, and it did that, and this kind of went really close and closer and closer straight down. Let's say there's even an asymptote. Let's say this was an asymptote here, and you couldn't draw anything beyond this, and there's an asymptote here, and you couldn't draw anything beyond this. Let's say it did something kind of like that. There's like tangent or something. And the vertical line test says we have to draw a bunch of vertical lines and see if it ever touches 2 points at once. So let's first get rid of this extra bit down here. That's a bit of a mistake. All right. If I also draw some vertical lines down this way, this vertical line only touches 1 point. This vertical line only touches 1 point. 1 point, 1 point. This vertical line only touches 1 point. This vertical line only touches 1 point. If I also draw a vertical line even beyond the asymptote, if I also draw a vertical line over here, this touches 0 points. Does that make it not a function? No, it's still fine. It's okay. You only run into a problem if you hit 2 or more points. And usually it's just 2 points. We often just say 2. But if it hits 0 points, if it hits 1 point, that's fine. The only problem is if it hits 2 or more points. The test is trying to see, can you hit 2 or more points by drawing vertical lines? And if you cannot hit 2 or more points by drawing vertical lines, then it is a function. And we can see that here. If we draw a line on the asymptote, we hit no points because asymptotes, as you may remember, don't touch points. They don't touch the line at all. They don't touch anything on the line. So this would be, so an asymptote touches 0 points. Anywhere that actually touches the line itself touches only 1 point. So we'd say no matter where we draw our vertical lines, it is only going to touch 1 point. So for our purposes and for our sakes, we can say that yes, this is a function because we can never draw a line and hit 2 or more points for this particular example. Now this example over here, the one we tried, the big problem that is from Khan Academy, that's still no. Yeah, we draw a vertical line and it hits 2 points and we're done, we're out. Okay, so that's kind of how a vertical line test works. Maybe one more example, just to really show you how one more way a vertical line might work. If I do this and it goes like this, just something like in that kind of direction. Let's say this was our graph. Okay. Now, if I drew a vertical line down here, then that works. It only hits 1 point. If I drew a vertical line over here, this only hits 1 point. So 1 point over here, 1 point over there. But if I draw a vertical line down here, down the center, I'm gonna hit 3 points. 1, 2, 3. And it's because I hit 2 or more points in this particular case. This would not be a function. It cannot be a function because it hits 2 or more points. So we'd say this is no. Because if I was to plug in input, let's say this is like 1. If I was to plug in 1, I could get 3 different numbers out. Press the 1 on the machine, on the machine, soda machine. I get 3 different prices out, which doesn't make sense. So we're gonna neglect that. We're gonna say that's not a function. Okay, let's move on to the next problem. And these next 2 problems are about domain specifically. Now, in order to really get to domain, remember what we were saying before about what domain is. Domain is always going to be all real numbers unless you break the function. Anything that makes it so that you can't reasonably figure out a solution for x, then we've got a problem. And then then we can't graph points for those values, and we run into an issue. Let's explain this more deeply, more clearly. The answer will always be all real numbers, as we can see right here. Domain, all real numbers except if something can break the function. So it's always going to be all real numbers. That's a fancy term for all real numbers, unless it breaks a function. We break the function unless you can divide by 0 or take the square root of a negative number. Those are the ways that we end up having problems. Okay. So if you can't ever divide by 0, do anything to the function, so you start dividing by 0, and if you don't see a square root that can go negative, then the domain's all real numbers. That's just the way it is. So let's look at this one. F of x equals x plus 1 squared. Now x plus 1 squared, let's see there's no division sign, so we can't divide by 0. Let's see there's no square root sign, so we can't take the square root of a negative. So this one is just all real numbers. All real numbers. And that's our answer. Simple as that. Let's look at this next one. This one says the square root of negative 2x. So we can't take the square root, and we can go negative. And here's the thing. So if you see a division sign, and here, that's actually before we can go with this. Let's go back up here. If you see a division sign, then the bottom, you set the bottom as not equal to 0. That will be your domain. This is the domain. If you have a square root of a negative, then you say that, because if you square root a negative, then you want to make sure you do everything to make sure that it doesn't ever go below 0. So you choose just the values that will make this go above 0. So you want to say, or even equal to 0. So you can say like the stuff inside the square root could equal 0. You can say the stuff inside the square root is greater than 0, but it can never actually be less than 0. So you go inside the square root and you say all that stuff, whatever it is. If you got the square root of say 2x plus 3, then you say, for example, that's not what this is, but if it was that, you'd say 2x plus 3 has to be greater than or equal to 0, because if it was less than 0, then it'd break the function and we'd have a problem. So you just set it as 2x plus 3 is greater than or equal to 0, and that's your domain. Well, we solve for x, and that's your domain. So we subtract it from both sides, subtract 3, and so you get 2x is greater than or equal to minus 3. And then you solve by getting rid of the 2, so 2 times x, so we divide by 2. Divide by 2. So it gives us x is greater than or equal to negative 3 halves. And that would be our domain. Cool? All right. Let's move on. So you got a square root of negative 2x. We've got a problem here because we have a square root. And so we need to find a way to make sure this square root doesn't ever become, the stuff inside the square root doesn't ever become less than 0. So what we'll do is we'll say negative 2x has to be greater than or equal to 0. Cool. All right, and then we solve that. So domain negative 2x is greater than or equal to 0. We're going to solve this, but remember, we're dealing with inequalities here. So there's a special rule we got to really make sure we pay attention to, because the inequalities work just exactly like an equation in every way, shape, and form that, as far as we're concerned, as far as the realm of equations instead of the realm of graphs. But except for one important rule, one very, very important rule. If you ever divide or multiply by a negative, the sign flips sides. So it goes from greater than to less than the greater than. And you can see why this is, because if you said 3 is less than 7, well, that's true. But if you multiply both sides by negative 2, let's say you multiply this by negative 2 times 3, and then you did, let's see, less than 7 times negative 2. If you multiply that out, you get negative 6 is less than negative 14. Now, if you were to, that might seem kind of reasonable on first glance, but if you look at this carefully, you'll notice, and you pull out a number line and start graphing this, you'd see that negative 14 is all the way over here, and negative 6 is over here, and then this is 0, and then you got 6, and so on. So you see that negative 14 is actually less than 6, or negative 6 is greater than negative 14. So whenever we do that multiplication, we've got to flip the sign and say, no, it's actually negative 6 is greater than negative 14. That's why the sign flips, is because when you go into the negative side, the things just kind of reverse. Everything, what's greater than or less than is reversed. Although 14 is a larger number than 6, when it's negative, negative 14 is a lot smaller as a number than negative 6. Okay. Sorry, I've been babbling on. Let's get this problem done. So if I divide both sides by negative 2, I'm dividing by negative 2, which means I have to flip the sign. So I'm going to cancel this out. And 0 divided by a negative 2, let's see, the 0 is above the fraction. And as Michaela said, it was like your head's above water. So it's still, the 0 can survive. So it's still a 0. So we'd say this is x. And then at 0, this would be equal to 0. 0 divided by negative 2 would have to be 0. But because we divided by a negative, this sign would flip to a less than or equal to 0. And that would have to be our answer. Cool. I think that's all the problems we have this lesson, this quiz. So if you have any more questions, just let me know. I'm here to help.